Anything else? Okay. Well, last time we were talking about this problem. The knapsack problem with repetition, which means you've got these items to choose from, and you've got an arbitrary, you can choose any amount, any number of any item. So you've got an infinite supply of each item to choose from. So you're trying to steal stuff that's the most valuable. Each time you got to choose which to pick, and so what we decided was we let K of W be the maximum possible value you can do if your backpack has capacity W. So that gives us our subproblem, because if our initial backpack has, say, capacity 100, and we take something that's weight 5, now we've reduced it to the problem of K of 95. That reduces K of 100 into K of 95. So the capacity of the backpack goes down as you choose things. And obviously, if you've got a backpack with no remaining capacity, you can't steal anything. And so that's the base case. The recursive case was just this. So essentially what this says is, for each item, you've got to decide which one to steal. So if you steal item I, your value will be V of I, plus the best you can do with the remaining space in the knapsack. And for all I, you try this out for each I, and you figure out which one is bigger. And that's the best you can do with this knapsack. So V of I is, let's say I is 3, so V of I would be 13. And let's say W is 20. In this case, then we would be saying 13 for the item we stole, plus K of the remaining space, which would be, if W is 20, it would be 13. 20 minus 7 is 13. Coincidence that it's the same. You would do the same trick for I equals 2, the same for I equals 1. Take the max. So you're just trying all the possibilities and seeing which one works out best. And there's just one catch. The catch is right here, which is basically saying, if your knapsack won't even hold an item of type I, don't consider it. You can't steal an item 3 if your knapsack has capacity less than 7. That's what this right here is saying. You only consider I's where there's room in the pack for the thing you're stealing. Right? So that's a recursive definition. We could turn this directly into a code, recursive method, and we could run it. But as W gets large, we quickly run out of time, because until the capacity gets small, for this example, you're branching 3 ways with each recursive call, and that multiplies that pretty fast. So we need to use dynamic programming technique to make it run faster. Okay? That's pretty much where we were last time. So let me just pause here and see if that's raised any questions. Yeah?
Order doesn't matter in this, right? Like
No.
what order we get stuff. So will that affect how we do our dynamic programming solution to this?
Okay, so yeah, order doesn't matter here in terms of this recursive definition. But the order in which you compute K can matter in terms of whether you run out of stack space or not if you're using recursion. We'll look at that in more detail shortly. Any other questions? So basically, to solve the problem, you've got to come up with a definition like this. And then you've got to decide how you want to attack it. Do you want to write it recursively and use caching? Or do you want to think of it in terms of filling out a table and dismiss recursion altogether? So let's look at what's involved here. So whether we create, one approach is to create a cache, and then as the recursion unfolds, the cache gets filled in. You can think of this as the cache in that case. For if you're solving K, if your initial backpack has a capacity of 11, then this would be all the cache you would need. Your cache, in the end, would have computed a value for K of 0, K of 1, K of 2, up to K of 11. And the answer would be right there. Or you could think of it in terms of, what we'll do is we'll use this up here to fill in the array. Think of this as an array and fill it in systematically. And when we're done, the answer will be there. So either you decide what order you want to fill in the array, or you just launch the recursion and let it get filled in whatever order happens in the recursion. Either way, you end up with these 12 values stored in an array or a hash map or whatever. But let's think about filling it in. So we're going to take the approach that these are actually array definitions. This is saying k of 0 is 0, and k of w is this formula right here. So where should we start if we're going to fill it in systematically? Should we go left to right or right to left filling this array in? Okay, we want to go left to right. We need to start with the base case and work our way up to here. Okay? Because if I pick an arbitrary element right here, what does it depend on? Does it depend on stuff here, or does it depend on stuff back this way? Right? K of w depends on things smaller than it. So as long as we have filled in everything to the left before we get to here, we're good. So let's do it. What should go right there? Yeah, that's just a base case. K of 0 is 0. Okay? Why do we put a 0 there?
Because there's no items that can fit inside of it.
Right, the smallest item weighs 3, and so we can't even consider putting items in the pack until we get up to here. So there's nothing to max over here, there's nothing to max over here. Now we're there. So I've highlighted that because this square here depends on that one right there. And then our formula tells us what to put here. We put, since the only one we can consider is item 1, because the others are all too heavy, we put here the value of 1, which is 4, plus what? K of 0, which is right there. Okay, so we get the 4. Now, what squares does this depend on? Actually, it doesn't depend on all of them.
It depends on K of 0.
Depends on K of 0. If we choose item 2, we're going to be interested in K of 0. What if we choose item 1?
K of 1.
We're interested in that one. And what if we choose item 3? You can't do that. So this square depends on these two. So we take the max of, let's consider 1 and 2. We'll do 1 first. We take the max of $4 plus what's stored there. So that's one thing that goes into the max. The other thing that goes into the max is, for item 2, is $7 plus what's stored right there. So which do we do? $4 plus 0 or $7 plus 0?
7 plus 0.
Right. So we get the 7. Now we go to the 5. Which of these previously computed squares does that depend on? Right. When we're considering item 1. Where will we look in this array?
1 and 2.
1, 2, 3 back, so we'll look at that square, and for item 2, we'll look 4 back, which is right here, and still not room for item 3. So this square depends on those two. So we repeat the process. Consider item 1. We take the max of $4 plus whatever in that square. That's 1. For 2, it's 7 plus whatever stored in that square. Take the max of those two things, and again, that's 7. Okay? For 6. 6 depends on these two squares. Okay? So item 1 is going to be $4 plus what's stored here. So that's 8. And item 2 is going to be $7 plus what's stored there. So the 8 is better. You see the game we're playing? By filling this thing in from left to right, viewing this as, rather than a recursive definition, just change all the parentheses to square brackets. Think of this as array definition. We got a way to just systematically move from left to right and fill the array. Now we get to here. Now we can finally consider item 3. There's room for that. And so at this point we care about that, that, and that. Okay? So who could walk me through this? How do we decide what to write in square 7? Go ahead.
So we have 3 items to consider. If
Okay.
we take item 1,
Okay.
then we will add the value 4 with the other item that you could also choose, which would be 7.
So the best, right, so if we pick an item 1,
Mhm.
that's $4 right there, plus the best we can do with a knapsack of size 4, which you previously viewed to be 7, so that would be 11.
Yep.
Okay?
If we took item 2, we would have a value of 7, plus the best we could do with a knapsack of size 3, which would be 4, so we'd have 11 total for that as well. And then if we took item 3, we would have a value of 13, plus the best we could do with knapsack size 0, which would be 0.
Right.
So we would want 13.
So we want the 13 here. Okay? This next one, right, is going to be 4 plus 7, which is 11. It's going to be 7 plus 7, which is 14. And it's going to be 13 plus 0. So we want the 14. So to fill in this box, we just take the max of 3 things. And the things we're taking the max of is always going to be the value of an item plus the best we can do with the remaining space, which is back here. So we go there are 3 things to look at. And in this case, let's see what the answer is. It's 14. So where did the 14 come from?
7 plus 7.
7. We take an item 2, that's 7, and then the best we can do with the remaining space, which is 4 squares back, is right there. That's 7 right there. So that's our 14. The next square depends on these 3. 4 plus 13 is one possibility. That's 17. 7 plus 8, that's 15. Or 13 plus 4. 17. Either way, 17. So we get 17. And then the last one here turns out to be 20. Because we get 13 for this square. Try to get it highlighted. We take an item 3, we get 13 plus 7. So that's 20. So we could just write this as a simple loop. We just march through this array, filling it in like I just did. Each step, looking at most 3 previously computed values, computing a max, writing the answer. Yeah?
So is the last element is our answer for the most amount of stuff we'll carry?
Right, so the solution to the overall problem is just K of 11, which is right there. Yeah?
So basically, the basic ones with dynamic programming is we start with a recursive solution, and then we get to this point where we have an iterative solution, or?
Yeah, so people have different opinions. Some people are good at this and they don't even think about the recursion after a while. They just think in terms of filling in a table. But the way I encourage you to approach it is write come up with this recursive definition, even implement it, test it out for small values, because it'll work for small values. If the values get too big, the recursion gets too much, it takes exponential time, because you're tripling the size of the recursion tree at each level. So the pure recursive method is not going to work. And then you think about how do I make it more efficient. The simplest way to make it more efficient is just to do what?
Memoize.
Just memorize it. That's sort of the no-brainer solution, and that's fine. You occasionally, if you don't think, sometimes you might run a situation where you run out of stack space. We'll talk about that later. But that just works. You don't have to worry then about what order. You just call K of 11, and the table will be filled in for you, essentially. The table being the memo, the hash table, the cache. Yeah.
So this takes linear space. Can we do better?
Okay. He says this takes linear space. Can we do better? Well, do you have an idea? What can we do?
Well, you only look at the past 7 values. If it's
Right.
important, it's not going to do you any good.
Right. So suppose that what are we doing here? The max. Suppose we're interested in K of 100. We wouldn't really need to keep the entire array. We could start throwing an array. Once you get over here, you don't care about the old values. So you can imagine doing it in less space. But these are examples of optimizations you can add after the fact. First is just getting the recursion right. So let's take the caddis problem you're doing this week. I've given you a multiple choice quiz that guides you to the recursive solution. So you should be able to take that recursive solution, assuming you answered the multiple choice part right, implement it in your favorite programming language, and pass most of the tests. All right? I got a question on caddis yesterday. It's my program works up until test, I think it was up until maybe the next to last or the one before that. And then it runs out of time. What's wrong? And the answer was, they weren't memoizing. It was just a pure recursive solution. So of course it was running out of time. The problem is designed so that you'll run out of time if you don't use dynamic programming. But the fix is very simple, just memorize it.
So we should do the caddis problem first and then...
No, you should do the multiple choice problem. And then you can almost, if you're using Python, you can almost copy and paste the mathematical solution. Almost. But, it's just a, a pretty simple recursion. And then while I'm on the topic, then I started getting questions yesterday from people. They did the third problem, multiple choice problem, and submitted it. And then they got to do 4, and 4 says, 4 is designed to parallel 3. And so they want to go look at you want to look at your solution for 3, but you submitted it. We all love Canvas, but it doesn't let you, the only way to look at your old quiz is to restart it. And if you restart it and don't do anything, it will be auto-submitted for you when the quiz closes. So what I meant to do and haven't done yet is to make a PDF of the blank quiz and post it. In fact, if someone wants to do that, send it to me. I'd appreciate it.
I believe that Canvas allows you to hide the correct answers, and then you can just unmute it. So
I go through this with every class. If it doesn't work.
Maybe you should just save it as a PDF before I click submit.
Yeah.
You just go back to it.
Yeah. People always tell me Canvas will do that, but anytime I've tried it, if it's a multiple choice question, it will show you, you can figure out what answers were wrong. Yeah.
I just wanted to say, it is multiple choice, and if you did the quiz, you can probably remember what the answers are just by looking at the multiple choice. So you can just open it and just resolve it in 2 minutes, and then...
If you want to resolve it,
Yeah.
Yeah, but realize that what happens when you open a Canvas quiz and don't submit it, leave it blank, what happens is a blank quiz is submitted when the quiz closes. And, we can, then it becomes a pain for us because you complain that you got a 0 and we have to go back and look at the previous quiz.
I mean, it becomes a pain for me.
It's a pain for Stephanie. Anyway. Okay, that's off topic. So, what's the complexity of this algorithm? Let's assume that, let's take the table as a constant size. So the only input is the parameter of k, W.
We're not going to just say the table's only 7 and we're just going to...
Well, I'm not talking about space complexity, I'm talking about time complexity. So what's the complexity of filling in this thing here for a fixed size table? So the only input's W. Yeah?
Wouldn't it just be O of W because you're doing a constant number of operations?
Okay. It's just O of W, right? You're doing a constant amount of work for each input, for each element. So it's proportional to W. Yeah?
But wouldn't you have to, like, if we had the same amount of items as we have, like, the weight that we're checking, wouldn't that make it x squared? Because you get the...
Yeah. Right. Yeah. So if you hold the table, I'm saying for a constant table size, it's W. If you say there are, let's say, k items in the table, then the complexity would be k times W. Because the amount of work you do at each element is proportional to k, the number of elements in the table. Now, does that mean it's a linear algorithm? We hold, again, holding the table size constant. Only inputs W. Okay, O of W. Okay, it's not. It's exponential. And I always have this discussion about this time in the course. Why is it wrong to call this a linear algorithm? Yeah.
Because we're saying that we're talking about the magnitude of W, we're not talking about the number of bits in W.
Right. When you describe the complexity of an algorithm, it is in terms of the size of the input, the number of bits in the input. How many bits does it take to represent W? Let's say W is 1,000,000. How many bits is that? 20. If it's 1,000,000,000, it's 30. So there are only log W bits in W. So the length of the input is log W. So if you take that right there as standing for not the absolute value of W, but as the length of W, the complexity is actually 2 to the length of W. So you can have a small input, only a 30-bit input, that blows this thing up. Suddenly it's taking 2 to the 30 steps. So it's exponential in the size of the input. Yeah?
So does that mean for multiplication, do we talk about the magnitude in terms of the magnitude, not in terms of number?
Yeah, when we talked about carousel multiplication, it was always in terms of the number of bits in the input. Complexity is n cubed, where n is a number of bits. So that was honest. That was an honest, not n cubed, and let's say grade school. It's n cubed for grade school, where n was a number of bits in the number.
Or n squared.
N squared. Yeah. Anyway, polynomial. Yeah.
So
So you have to be careful. Yeah.
So if we talked about it in terms of just size, then it would be like log of n, all that squared.
Yeah, if you talked about, if the cost of doing grade school multiplication on x and y, where x and y are the magnitude of the number, is log x times log y. The number of bits in each. Okay, now, what if you just wrote this recursively? What we did was you sort of imagine just taking a loop and wrapping around this. The loop goes from 0 to 11, and we just use this as the directions on how to fill in each array element. But what if we just wrote this recursively and called k of 11? What would happen? Yeah.
Well, without the table, it would go back and compute all of the values that it
Yeah.
was before that.
So we call k11, it would recursively call what?
7, 8, 9.
It would call k of 8, k of 7, k of 4. All right? K of 10 would call k of 7, again, k of 6, k of 3, and so on. So stuff would happen, but the reason it wouldn't take exponential time is that the first time we computed k of 8, we would save it, and the next, or k of 7, we would save it, and the next time we just look it up. So this table would get filled in some order. What order would it get filled in? If you think of this as the cache. It'd still get filled in left to right. Because you can't possibly compute something until you've computed the things it depends on. Roughly left to right, actually, it would start, it might skip some, but eventually everything would be filled in. The only possible thing that could go wrong relative to the iterative approach is you call k of 11, the recursion is going to recurse all the way to the base case, or close to one of these things. So that's going to take some stack space. What if we're computing k of 1,000,000? It's going to recurse all the way down to these base cases before it fills in anything. So you could run out of stack space. So how could you prevent running out of stack space?
Tell the compiler to give you more stack.
He said, tell the compiler to give you more stack, but suppose that there's just not enough stack, not enough memory. Yeah? You could do it iteratively.
You could recurse.
You could force it to fill it. You could write the recursive definition, and then instead of calling k of 11, you could just write a loop that calls k of 0 and k of 1 and k of 2. You could force it to fill in the cache in this direction. So if you recognize what's happening, you can just write a loop. Instead of calling k of 11 and letting it fill in itself, just call them in this order. It takes a little bit more work, but that way the recursion never goes more than a couple deep. Yeah?
Could you, like, split it in half instead of starting all the way from the left to 7 to the right? Could you, like, call, like, so if it were k of 12, now it's too much stack space, you call k of 6 first?
Yeah. I mean, you could do that. You could call k of 6. But if you if you've recognized the problem, that is you're running out of stack space, the remedy is either do it iteratively or just force it to approach the problem in a certain order. Ideally, you just call this and let it unfold. Sometimes that's not going to work, so you need to do that. Okay, here's another version, knapsack problem without repetition. So now, you're only allowed to take at most one of each item. Okay. So we've got to come up with a way to characterize the subproblems. So again, we're interested in what's the best you can do with a knapsack that holds W pounds. But we've got to turn that into subproblems. And it's a little bit tricky. This is how we'll do it. We're going to let K of W and J. So now there's sort of a two-dimensional problem. K of W and J is the maximum possible value of loot if the backpack has capacity W, and we are restricted to choosing from among items 1 through J. So if we had a knapsack of capacity of 100, what subproblem do we want to solve to get the overall solution to the problem? What two parameters would we pass to K to get the answer to the problem we care about? Capacity of 100, and there's our table. Yeah?
K of 103.
Yeah, K of 100, comma 3. What's the best you can do with a 100-pound knapsack if you're allowed to choose from items 1 through 3? Now, you may be wondering, what's the second parameter for? Why is it necessary? Essentially, there has to be some memory. We've got to have some way of remembering whether we chose an item 3 or not. You only choose one. So let me show you how that works. K of 0J. So what's the best you can do if your knapsack holds 0 pounds? Doesn't matter what J is, that's 0. Okay? What if you got a knapsack that has some non-zero capacity, but you're not allowed to choose any items? Presumably because you've already chosen those items, right? That's 0. What's K of WJ? Okay, this is where we have to get more creative. I want to define K of WJ. So your knapsack has capacity W. You're allowed to pick items 1 through J. And furthermore, W is less than W and J. In other words, there's not room for an item J. So the way we're going to approach this problem is that in the recursive case, K of W and J, there's going to be one choice. Do we take an item J or do we not? Right? So in this case, we can't even take an item J. The only possibility is we don't take an item J because there's not room. So what would K of WJ be then? What were we defining it as?
K of WJ minus 1.
Exactly. So in that case, we're asked, what's the best you can do with capacity W? You're allowed to choose items 1 through J, and our strategy is always going to be, whenever we're posed with a question like this, the choice we're going to make is we either take a J or we don't. In this case, it's impossible to take a J, so it reduces to this problem where we're no longer considering items of ID J. And the other possibility is that it would be possible to choose a J. So now we can either choose a J or we can't. So how do we decide what to do? How do we decide whether we need to take an item J or we don't?
We take the max.
You take the max of both possibilities. You consider both possibilities and we take the max. So we take the max of two things. What's this correspond to?
Not taking it.
That's what happens if we don't take an item J. This is where we did take the item J. We get its value, we reduce the size of the knapsack, and we're no longer allowed to consider items of type J. Yeah?
Does this mean that the table needs to be sorted, where if J is the largest J corresponds to the highest weight, or no?
No, the table doesn't have to be sorted in a particular way. He's meaning that table right there. We could put them in the opposite order, it would still work. We could put the lightest item first. Okay? So again, I just said, it's my strategy to define that two-parameter function. And I just told you that my strategy is that when we're faced with when we got a j parameter here, we're just going to choose at that point whether or not to pick an item of type j, and that's our last chance. Right then we choose whether to take item of type j, and then we reduce the problem so we're not even considering that row of the table anymore. Okay? And so that's one possibility. That's the other. If the backpack is small enough, we just use the one possibility, right? Which you can't take an item j at that point. Okay? So, let's suppose we want to fill in a table. So we would create a two-dimensional array. This is, again, we're interested in k in a knapsack of capacity 11. So this is all the possible values of w. That's all the possible values that j can take. We've got to fill in the table. So let's get a little practice first. That green square right there, which squares does it depend on? If we had to compute k of 9, 3, what other squares in this array would we look at?
The one immediately below it.
The one immediately below it, what does that correspond to?
K of w j minus 1.
Right. We're always interested in, if we're in the recursive case, we're always interested in the square right below us. That corresponds to, we decided not to take an item of type j. What else does it depend on?
The one below, and then to the left, 7, 4. And
Exactly. The other one is, again, on the row below, but 7 to the left. 7 being the weight of item 3. So we take, those are the two we look at. We look at that square, we look at that square. Okay? Let me stop here, see if that makes sense. We're just basing it directly on this. The one yellow square is, we have, the green square, k is 9, and w is 9, and j is 3. So one possibility, we look at k of 9, 2. That's the one yellow square. The other possibility is you look at k of 2, 2. That's the other one. Yes?
How come we don't have to consider items 1 and 2 right now?
Well, we're going to consider them next. See, at this level of recursion, we are deciding whether or not to take an item of type 3.
Ever.
Right. Once we've made that decision, now we've reduced it to where we're considering fewer items. So at lower levels of recursion, we choose items 2 and then item 1. Yeah?
So is the v of j down there, is that the green square?
No, v of j is the value of item j in the table up there. 13. Yeah.
So, using this dependency, we need to fill from the bottom up.
Well, again, if you were going to, where's our answer going to be in the end if we fill in a table like this?
it's going to be a green square.
Upper right-hand corner. So if you're taking the strategy of iterating and filling in the table systematically until you get up to that upper right-hand corner, again, you start with the base cases and work up. So you could fill it in row by row, left to right.
So in the next layer, it's going to be the one below.
Well, okay, so let's do this. What squares should I color yellow here? What squares does that green one depend on?
The one below.
The one below it, always.
And to the left.
But the one 7 hops to the left on the second row is off the end, so we would be in this case here, so we don't need to care about the one right there. What about that one right there, that green one? What squares does it depend on?
One below and 7 to the left.
So it's the one below, but it's not the one 7 to the left. Because now j is 2, so it's the one 4 hops to the left, because the weight of item 2 is 4, so it'll depend on those two. What about that one? What's it depend on?
Below and 3 to the left.
Below and below and 3 to the left, because that's an item 1. Okay? So, if you're only interested in computing, suppose you did this recursively. You just took this recursive definition, you called k of 11, 3. Which squares would the recursive solution solve? Yeah?
Ones that are linear combinations of the weights.
You said the ones that are linear combinations of the weights. Okay, Sort of depends what you mean by linear combination of weights, but I can buy that. We want to compute that. What squares does it depend on? What recursive calls would that one make?
Only two.
One below.
One below.
The one below and the one below and 7 hops to the left. Okay? Now, let's take the one on the right that we just added. What recursive calls would it make?
One below, 4 to the left.
Below and 4 to the left. And staying in the right-hand column, what recursive calls does that make?
One below and 3 to the left.
Okay? Then, let me see where I am.
Go back up one layer and then go to the left.
Well,
Yeah, so this one right here in column 7, what recursive calls would it make?
One below and 3 to the left.
All right, we would do that. What about the one in row 2 up there in column 4?
One below and 1 4 to the left.
One below and 4 to the left, and there are a few more to fill in, but basically that's it. So if you launch the recursion, it would calculate just the yellow squares, store them in the cache, and return the answer without ever touching those white squares. If you did it iteratively, you would fill in all the squares. So, what does that tell you?
Recursive might be more efficient.
Sometimes the recursive version can be a lot more efficient
But if all of you,
if it's got a situation like this, where it's not necessary to compute every simpler thing in order to compute the overall answer. Now, on the last slide that we're looking at, the other problem, you had to fill in the entire table, whether you did it iteratively or recursively. Actually, no, that's not even true. You'd see the same effect there. I take that back. Here it's more obvious, though. Yeah?
If the distance between the weight of each item was only 1,
Yeah.
then you would have to fill in.
Yeah, well, right. If the weight of everything was 1, you would have to fill in the whole table.
Or if even it was 1, 2, and 3.
Well, 1, 2, and 3, you would be skipping some on the top row. You'd only look at every third one in the top row and every second one in the next row, and then every one in the
For
other.
this one.
Yeah, for this one.
For the other one, you'd have to.
Yeah, it depends on the input. But the point is, sometimes the memoizing can beat the pants off off the iterative version.
isn't the whole bottom row just zeros?
The whole bottom row you can just fill it. The whole bottom row is zeros because you can't, and the whole left column is zeros because that's the base case. Okay.
any way you can predict whether or not is there anything you can do?
Well, you can predict this is going to happen just by, you have to sort of do this exercise we just did and realize that except for the potential problem of running out of stack space, the recursive version is going to be superior.
Yeah. So if it's really complex, you can't think of a way to model it, then maybe just implement it both ways if you can figure out how to implement it iteratively and then profile.
Yeah, you could profile it. I think the strategy ought to be write it recursively, memoize it. If that's good enough, great. If it's not good enough, think harder. Okay? And if you take that strategy on the caddis problem, you'll find out that if you write it recursively, memorize it, that works. It does. Unless you're using Python and running out of stack space, in which case you have to know how to ask for more stack space. But Anthony has already posted that. Okay, so this is what we just talked about. We can choose between memoizing a recursive solution or iteratively filling out a table. Traditionally, the term dynamic programming refers to developing a strategy for filling in a table. But the term is from the 50s, so it's an old, sort of an old term. Memoizing is usually easier, but people that get good at this can often skip the memoizing step, and they just immediately conceive of the solution as filling in a table, and they just write that way from the start. If all possible subproblems must eventually be solved, tables are going to be faster because you eliminate the recursion of overhead. And like we just saw, if only a small number of subproblems must be solved, memoization will be faster, as long as you don't blow the stack. So we've looked at a bunch of examples here. So let's look at how they let's think about them in terms of these ideas right here. So this was the rod profit, the very first one we looked at. Must all subproblems be solved? Yeah, all subproblems have to be solved. So this is the, that's the pure recursive version without memoizing. This is, to make it iterative, you see all we had to do, you can see the yellow we added. We just added a loop around this to fill in the table. Okay, well, that's easy to do. Okay, only some problems need to be solved. So that was our use case for memoizing. But you got to be careful not to exhaust the stack. So this is our rod problem again. We're starting with a piece length of n and working down to the bottom and making the recursive call to compute the max profit. That can run out of stack space. What's a simple fix to prevent this from running out of stack space? How can it run out of stack space?
Because the recursive def is scales memory.
Right, so we're starting at n, and then we're going to call rod profit, and then -1, and then rod profit.
So,
Yeah.
instead start at 0?
Yeah, just reverse the order of the iteration. This is working from the top down to the base case. Just flip it around.
And then can we call it getaway?
What's that?
Do we call it getaway once we're done?
No, we just do that, and it fills out the same table. It just fills out in different order, and it does it in a way where it doesn't ever have to make deep recursions. So, you know, there's your recursive version. That's not memoized yet, but it would need to be memoized. But if you turn around that way, you're just filling it out so that you're solving and storing, if you memorize it, the simple cases first. So that when you get up to the more complicated cases, you've already solved the simple cases. So that's just a trade-off you can make. So it takes you know, it's not always automatic. You have to think of, if something goes wrong, you got to figure out what it is. And see if you can do something about it. All right. Any last questions before we change topics? Yes?
I still just don't quite follow how looking at the bits means it's an exponential algorithm rather than linear.
Okay. So when you sort an array and we say the algorithm is n squared or n log n, what is n?
The length of the array.
Right, the length of the array, the size of the problem, number of bits in the problem is proportional to n. Okay? We always want to express complexity in terms of the size of the input. Okay, so if a parameter is 1,000,000, what's the size of the input? How many bits?
It'd be log of a million.
Right, it's 20. Log of 1,000,000 is 20. So when you're trying to express the complexity of an algorithm that takes an integer as its input, you need to express it in terms of the number of bits in the integer, which is the log of the magnitude. And so in the problem we were looking at, k of w was an integer. And so saying that it's linear in w is true, but if it's to accurately characterize complexity, you have to do it in terms of the size. So the correct thing is it's O of 2 to the size of the input.
Okay.
Another way to think about it is, let's say you compute k of 20, and that takes 10 seconds. Now, how long is it going to take to compute? You do k of 1,000,000. Okay. Now you do
40 bits. Should be a trillion.
I'm trying to think of my example here. So k of 1,000,000 takes a certain amount of time. What happens if you double it? K of 2,000,000. So you increase this length by 1 bit. You've doubled the magnitude. What's going to happen to the running time?
It's got double its linear time. But the magnitude has only increased
Right.
by log n.
So you increase the length of the number, you increase the number of bits by 1, and yet the running time doubled. That's exponential. So every time you double the magnitude, you increase the number of bits by 1, the running time doubles. That's characteristic of an exponential algorithm. Problem size increases by 1, running time doubles. Exponential. Yeah.
So what if we, instead of expressing our numbers by saying kind of an exponential notation, what if we just said like 2 is 1, 1, and 3 is 1,
Right.
1?
So there is this thing. You could instead of using binary to represent your numbers, you could represent them using what's unary, which no one ever uses, where 1 is the only symbol is 1. So the number 1 would be 1 bit. The number 2 would be 2 bits. The number 3 would be 1, 1, 1. A million would be a million bits. Well, okay, if you use unary notation to represent integers, yeah, then our solution is linear. It's honestly linear. That's sort of making your numbers exponentially large in order to get a linear time output. It's kind of stupid. Okay, let's take a break and we're going to change topics. Problems. At first glance, it looks like it's pretty restricted because what it is, it's like it says up there, it's a general approach where you can solve optimization problems in which the constraints and the optimization criterion are linear inequalities. So I'll show you what that means in a second. What we'll be doing is we'll be learning how to express problems as linear programs. And then we will just feed our linear programs into a standard algorithm and get the solution. We won't spend much time learning how that standard algorithm works, so it's a little bit different from other topics we've looked at. We're just going to use a canned program to solve our linear programs. One thing that we'll talk about next time, which is kind of neat, is any optimization problem that you can solve in polynomial time can be solved in polynomial time with a linear program. So in a sense, linear programming is sort of a completely general way of solving polynomial time problems. It doesn't mean that the linear program will be just as efficient as a tuned algorithm for something like, say, so in other words, we could express a shortest path problem as a linear program. But it doesn't mean that the linear programming could be solved as efficiently as Dijkstra's algorithm would solve the problem. But so it's mainly a theoretical interest. So anyway, here's our first example. You've got a chocolate company that makes 2 products, Matin and Nuit, and they've got to decide on how to make the most money. So they know they can sell X boxes of Matin for $1 per box. They can sell Nuit for $6 per box. They've got an upper limit of each type of candy they can sell. They know their market. And they can produce at most 400 total boxes per day. What should they do to maximize profit? Now, it's not too hard to see they ought to
Sell 300 units?
make as much of the expensive candy as they can, and then use the rest of the capacity to make it cheaper. But this is one place where linear programs are used is for businesses solving problems like this, except the constraints, lots of constraints. Instead of you choosing solving for X, 1, and Y, and for X and Y in this case, the number of each kind to make, there are going to be all kinds of inputs like labor and regulations and so on. So you can make a really complicated linear program with hundreds of variables, and then solve it to try to find out what's the best way to steer your business. So we can express all this with linear program. So what we do is we let X and Y stand for the number of boxes of each type of chocolate that we're going to produce, and you create linear constraints. So the constraints use X, Y, and constants. What makes them linear? What makes this a linear constraint? Yeah.
So you can't have like x times y
Right. You won't see x times y.
or x times x?
Or x times x, right? It's just going to be constant times x combined with a constant times y. And then we use inequalities. So this says that you can't make negative number of either kind. You can't, where did this come from?
Can't make more than
We
200
can
boxes
get
a
it.
month.
Well, you can make more, but you don't want to, because you can't sell more than 200 units of x. You can't sell more than 300 units of y. Yeah?
Well, you can make a negative, right? So you can, in that case, you just shift everything with a bias. And then
Well,
shift-
but just in terms of this problem, it doesn't make sense to talk about producing negative 10 boxes of UE. So, and this comes from the Capon, this is your production limit. These are sales limits. This is production limit. You can't make more than 400 total boxes. So those are the constraints, linear constraints. And then there's something you're trying to maximize or minimize. That's called the objective function. In this case, we're trying to maximize profit, and x plus 6y is our profit. $1 for Matan, $6 for UE per box. So we're trying to make this as big as possible, subject to these constraints. And in general, in a more realistic one, like I said, you might have hundreds of these constraints. There'd be hundreds of variables, thousands of constraints, and some complicated objective function. But the objective has to be linear, again, a linear combination of x and y. Okay? So that's what I mean by linear programming. So let me see if there are any questions about this linear program before we solve it. Yeah.
It seems like in order to make the $6 profit per box, you have to sell Y boxes. So it's not $6. Like if you only sell one box. I'm a little bit confused about what the selling Y boxes. You have to sell Y boxes before you
Right.
can
We
make
know
$6.
if we can sell 200 boxes of one and 300 of the other per day.
Right.
So if you make it, as long as you don't make more than 200, you can sell every X. I mean, you can sell every one of this.
Okay.
And as long as you don't make more, as long as you make more, if you make no more than 300, you can sell each. You can sell all of the ones you make of the other kind.
Okay. So even if you only sell one box, you could make $6 off of it.
For UE.
Okay.
Yeah. Each box you sell is $6 a profit.
So there's not a minimum that you have to sell in order to make
No,
that much profit?
No, right. But in a more realistic situation, there would be, right? The first few boxes would be more expensive, per box than making everything. So you can imagine having a much more complicated linear program. Yeah?
Can you sell half a box or?
No, we can't sell half a box.
So doesn't that kind of make it's kind of tricky if like you have kind of fractional weights?
Right. So that is an issue. So what he just pointed out is we're not interested in getting an answer that says your best strategy is to make 100.5 boxes of one and 200.5 boxes of the other. We want the answers to be integers. Linear programming, you're using real numbers. There is a variant of linear programming called integer programming, which is absolutely the same as this, except all the variables are constrained to be integers. Linear programs can be solved in linear time. In polynomial time. Integer programs, in the worst case, require exponential time. So linear programming is more complicated than integer programming is more complicated than linear programming. So what we do is we just express it as, we express it this way, and if we happen to get non-integer answers out, you just, round them slightly. So you might not be quite getting the optimum, but you're close. You round them to integers. A lot of times it doesn't matter. Okay, so to solve it, we got to solve that. There's something on the web called LP-solve. So I downloaded it, installed it. It's a linear program solver. And you just put the program in, that's the format that it wants. It wants to see, first of all, either max or min right there, followed by a colon, followed by the objective function, followed by a semicolon, followed by the constraints, all terminated by semicolons. And so if you put it in that format, you can, or I can do a copy here. So I can take this, copy this program. Here's my LP solver. I've got it running. I just paste it in and run it. And I look at the result, and there it says, the result is I make 100 of the first type, I make 300 of the second type, and then at the top line there it says the profit will be 1900. So that's what LP solvers do for you. Yeah?
Did you use linear algebra to solve this?
I'll sort of sketch how it's done, how the solution is done. But we're not going to study in great detail the algorithm that's used. So you'll eventually have an assignment, probably sooner than later, where you're going to use LP solve or something similar to solve things.
So we're using LP solve, we're not writing LP solve.
Right, you're not writing LP solve. Right? You're just a user this time. Okay, so when you write a linear program, it turns out that if you put all the constraints together, if you've got two variables, you are describing a convex polygon on the plane. So this pink region right here is called the feasible region. Any point in this region satisfies all the constraints. So you can see x is greater than or equal to 0, so there's nothing this way. Y is greater than or equal to 0, so that rules it out. So all we're left with is a quarter plane. And with this next constraint, x is less than or equal to 200, that gives you this line. Y less than or equal to 300, that gives you that top line. And then x plus y is less than or equal to 400, that gives you that diagonal line. So the constraints, with the constraints, you end up with the feasible region. Yeah?
Oh, no, I'm doing...
Okay.
Right.
Now, the feasible region could be empty. How would you come up with an empty feasible region? Yeah.
Say x has to be greater than 300.
Right, we could add like x has to be greater than 300 or something. You could add so many constraints that there are no points that satisfy all the constraints. In that case, the linear program has no solution. Another possibility is you could end up with an infinite feasible region. For example, suppose we didn't have these last two constraints. What would our feasible region look like? It would just be, it would go all the way to infinity. So in that case, it's possible that there is no way to maximize the objective function. Because in this case, suppose that was a feasible region. It went, it started here, it had these two lines, it just went to infinity. You couldn't maximize x plus 6y because you just keep making x bigger and bigger forever. No, y. Y, you keep making y bigger and bigger forever. But generally, when we create these our linear programs, we're going to have a finite region. Now, what if you added 3 variables?
It would just be a convex dimensional region.
Now you end up with a convex polyhedron, a 3-dimensional solid in 3 space. Okay? Again, it's convex. Convex just means there's no chunks bitten out. That if you draw a line from any point to any other point, it'll stay inside the region. If you had a jagged edge here, you could have a line from one point to another that entered and left, entered and left. But we're always going to have convex. So what if you have 4 variables?
It should be a convex.
It's still a convex, I don't know what the word is, it's a 4-dimensional convex solid, whatever the word for polyhedron in 4 space is. And if you have 100 variables, it's in 100D space. It becomes impossible for us to visualize, but mathematically it's just as sensible. Yeah?
So why is it convex? Like you can't have like a constraint like x plus y if x is greater than...
Right. If you don't have piecewise functions. Any constraint, in the 2-dimensional case, any constraint is going to be, any inequality is going to be a half plane. And you're just intersecting all the half planes. And the intersection has to be convex. Okay, so we just said what a feasible region is. So the point of the linear program, the constraints describe the feasible region, and then the algorithm has to figure out which of these pink points maximizes that function right there. Okay? So let's graph the objective function. So I just graphed, so the thing we're trying to maximize is x plus 6y. So let's just pick, I picked 180 just for the heck of it. This is the line where x plus 6y equals 180. All right, you can see it up there. X plus 6y is 180, that's y equals 30 minus x over 6. So you get this thing that crosses at 30 and has slope, whatever that is, 1/6 or minus 1/6. I forget. So every point on this line here that's inside the peak region, the objective function there has a value of 180. So is that the best we can do, 180? Could we do 200?
Yeah,
What would 200 look like if we plotted x plus 6y equals 200?
it's a parallel line just above
A
it.
parallel line a little bit higher up. So essentially, if we just keep pushing this line up, we keep getting better and better results for our objective function. But we can't keep pushing it forever or we leave. Okay? So we go up as high as we can, and right then we left the region. Now, where was that line when we left the region? What was the last point it touched?
It's that corner right there.
X equals 100, y equals 300.
Right, that little corner right up there. I claim that no matter what the objective function is, the last point it touches when it leaves the feasible region will be a corner. Okay, think about any line you want to draw, any slope whatsoever. You let it move up, in the case of maximizing, or move down in the case of minimizing. The last place it touches is when it leaves the region, it's touching a corner. Yeah?
Well, what happens if you have a flat line? When
Okay.
you touch a line at the top,
What if we had a flat line and we started raising it? What's the last thing it would touch?
it's that whole top line.
It would touch that corner,
And
that corner, and everything in between. But it is touching a corner. The last thing it touches is a corner. Okay, so I'm not making a mathematical proof. I'm just sort of appealing to your, just to your sense of space here. That any line we draw and start moving, because it's convex, the last place it touches will be a corner. Okay? So, what does that suggest about a way to solve a linear program? Yeah?
check the corners.
Check the corners. All we have to do is look at the corners and figure out which is the max. It turns out that's not good enough because it is in this case. What about in 3D? What's our objective function look like in 3D?
It's a plane.
It's a plane that's moving through a three-dimensional solid. And again, when it exits, it's going to be at one of the vertices, one of the corners of the solid. In 100 space, right? You got a 100D solid and you got a 99D hyperplane. The problem is, as D gets bigger, as the number of dimensions gets bigger, the number of vertices you have to consider can grow exponentially. So it's not enough just to say you look at every corner and see where it maximizes. It turns out there's a better way to do it. We'll talk a little bit more about that next time. But for right now, I'm happy if you just understand what's happening here is, you just have to consider the corners.
Does the objective function have to be a linear function too?
Yeah, the objective function has to be linear.
So all of it's linear.
So that's the illustration in this case of when that objective function leaves. So the maximum is right there at x is 100, y is 300, which is what I found. Okay, we've said all that stuff. Okay, let's do another program here. I'll let you think about it. Now we introduce another kind of product. So we got x, y, and z for Martin, Louis, and Lux. It's all French. So you see the constraints. How would you express those constraints? So, and what is the objective function? Yeah.
So the objective function would be 1x plus 6y plus 13z
Okay, so we're trying to maximize profit. So
is less than or equal to 400.
Well, no, the objective function is not an inequality. The objective function is just how much profit you can make, in this case. It's trying to maximize profit, which is 1x plus 6y plus 13z. All right, and then the rest of the program are constraints that constrain. If there weren't any constraints, you just make as many boxes of each, as many boxes of the most expensive as you can and solve it, but they're constraints. So someone else tell me, how would you express constraint 4?
X must be less than or equal to 200.
Right, x is less than or equal to 200.
Y must be less than or equal to 300.
Right, y is less than or equal to 300. Right, someone else tell me how to do constraint 5. Yeah?
X plus Y plus Z must be less than or equal to 400.
Right, and what about the last one? Yeah?
How many minutes are in
Does it matter actually?
It doesn't matter. You can only run the packaging machine for 600 minutes.
there per day?
So yeah,
X plus 3, or sorry, Y plus 3Z is less than or equal to 600.
right. Y plus 3z is less than or equal to 600. So the total amount of time packaging has to be less than or equal to 600. Okay? So there's our objective. There's our constraints. If we were to graph it, and I haven't, it'd be a three-dimensional thing. I think there's a picture in the book, sort of a perspective of what it looks like. The objective function's a plane, and the maximum is at some corner of this 3D solid.
Do you have to put that X is greater than 0 and Y is greater than 0 and Z is greater than 0?
Well, what would happen, what if we didn't have these constraints here? What would our feasible region look like? It would have, in addition to the, like if we go back, we can go back when we can actually visualize. Suppose we didn't have these constraints here. So we would still have those corners there, but then it would continue all the way down here, and it would continue all the way over there, and down here.
I don't think everyone heard the question.
What's that?
I don't think everyone heard the question.
Okay, the question is, what if we didn't have these two constraints? We would have an infinite feasible region, that is true, yeah.
We'd be allowed to make negative amounts of boxes of chocolate, which is not possible.
Well, you could argue that it's sort of a non-physical thing, but it's a legal linear program, so we can talk about it. So the feasible region is infinite. Does that doom us?
Depends on our objective function.
Yeah, our objective function is still, okay, that line, in that case, there's only 3 corners, and we're good.
2.
No, that's right, 2. Right? Only 2 corners, and one of them is still going to be the max. So we'd be okay. And we could take LP solve and see that. So linear, an infinite region doesn't doom you. Now, if it were infinite in the other direction, and we're trying to maximize, it wouldn't work. And if we were trying to minimize the objective and we eliminated these lower constraints, that would be bad, because it wouldn't be able to find a solution. Okay, so that is, we could take that, put it into LP solve, and be done. All right, here's another example. This is an example of what's called a network flow problem. And the idea is, assume you're trying to pump oil through a network. And the oil starts at S. So S is like the well. And T is the tanker, maybe. And you've got to get oil over this network from S to T. And the idea is you want to, you can pump from S to A, or from S to B, or from S to C. And then from there you can, from C you can pump to E and so forth. So it's directed graph. The numbers on the edges are the maximum amount per hour, let's say, the number of units of oil you can pump per hour. So you can't just start at S and start pumping. Let's assume you got all the oil in the world at S. You can get as much oil as you need. What would go wrong if you just pumped everything at maximum capacity? Let's say you pumped 3 units from S to A, and 3 from S to B, and 3 from S to C.
You get stuck along those bottlenecks.
What would happen at port A? Yeah.
Yeah, you'd waste 1 unit of oil because you can only go 2 units from A to B.
Right, the pumping station at A is getting 3 units in, but it only put 2 units out, so it would explode.
They're really getting 6 in, because they're getting another 3 from B.
All right, so B in the meantime is getting 3 and sending it all to A, so yeah, A is in trouble. So what we want to find is, we want to maximize the amount of oil arriving at T, subject to the constraints that, well, what are the constraints? You can't pump more than 3 units per hour from S to A, and A can't be receiving any more than 2 units per hour, right? So we don't have time to finish this today, but the idea is we could describe this problem, we could take these constraints that we've sketched and make a linear program and solve it. So this this is no longer selling chocolate bars, this is solving a real problem. There are algorithms, dedicated algorithms for solving maximum flow. We can describe linear programs, so we'll write it next time.